Okay, this lesson we're going to continue our discussion of vertical motion. So this is vertical motion part 2. Okay, from the previous video, you learned that all objects accelerate at a rate of roughly 10 meters per second squared. That 10 meters per second squared is an estimated value for how quickly things are going to change the rate of their velocity. In reality, what we're going to use is a rate of 9.81 meters per second squared, which is equivalent to 32.2 feet per second squared. Okay, the 9.81 again is a more accurate value than the 10 meters per second squared. What we're going to continue to do is look at a couple other scenarios for vertical motion. One is a throw-up problem, and the other is a throw-down problem. To illustrate these differences, take a look at this applet based from Web Physics. As you learned in that last video, when you just have something free fall, that is nothing giving it an additional velocities, the object is going to accelerate downward at a rate of roughly negative 10 meters per second. I've got 3 different graphs: a position time graph, a velocity time graph, and an acceleration graph. Notice how from our position time graph we know the object's accelerating because our slope is changing. Our velocity graph, we start at a 0 meter per second value, and we are gradually increasing our speed. Our acceleration rate is holding constant, again at that approximate 10 meters per second squared value. If we watch the animation again, you can see that the object again gains speed each time, and it's covering more and more distance each time. When I toss something upwards, what I'm doing is I'm giving it an initial velocity or thrust in that upward direction. Notice how it gradually decreases how much distance is covered each time, and then gradually increases how much distance is covered each time. On our position time graph, you can see that we're starting to cover a lot of distance in the beginning, but then our slope gradually slows down to 0. This point right here where the cursor is at is that top height that the ball reached. Then it starts to cover more distance, but now on the way downward. My slope gradually gets steeper, so it's getting bigger and bigger and bigger. Now take a look at this velocity graph. We start with having a positive velocity. That indicates that we tossed it upwards. The velocity gradually decreases until we get to that 0 velocity. Then it gradually increases again as we go down. All the while, though, we're maintaining that rate of negative 10 meters per second squared. Gravity is constant no matter what type of situation we deal with. The other type of situation we have is the throw-down problem. Okay, the throw-down problem just means that I've got an initial velocity downward. Notice how the position graph, we gradually increase how much distance we're covering each time. My velocity keeps getting bigger and bigger and bigger, but my acceleration rate stays that constant negative 10 meters per second squared. The only thing that this means for us is when we deal with our equations, we now have an initial velocity to include. If I have an initial velocity upwards, that VI is positive. If I'm throwing it downwards, it's going to be negative. So this V would stand for the velocity at any point in time. We also have our equation for the displacement of the object, whether it's going up or down. Again, initial velocity is positive if it's upwards, negative if it's acting downwards. Okay, come ready with questions to class next time, and we'll go over these in more detail.